And it's a great honor for me to be here to give a talk to you. And it's also a great honor to be the last one. Hopefully, you will remember it the best. And I know all of you are tired, and me too. So what's the problem? Let's make it quick. Now, just a relaxing slide for you. I came from Denmark, as Pablo just said. And I came from this unknown city called Odense. And just few random pics about Denmark, what it is famous for. Yes, you can read it. Now about my talk. I will mainly talk about transmission mode s-SNOM. So who of you work or kind of have it nearby the transmission type s-SNOM? Can you just put the hands? Oh, it's surprising. It's not just me. Okay. But it will be also about pseudo-heterodyne, which is called CW or imaging module. So again, let's put the hands up. Who has this pseudo-heterodyne? It's also for reflection one. Okay, good. It's like half, let's say. Finally, it will be mainly related to visible and near-infrared range. So please put your hands up if you are working in this range. Okay, still not bad. So I'm not alone here. And, but I'm here in the middle, but if you are not there in the middle, don't be disappointed, because the ideas and tips and tricks which I will tell you, can be applied beyond this central spot. It can be applied also in other ranges. And also, like my talk might look like promotion of this transmission module from s-SNOM, but I can assure you I have no benefits, no interest in near-spec, but it is simply superior for what I will talk today. So transmission mode s-SNOM, how does it work? I think it was mentioned by Rainer, maybe someone else. Here, the difference that illumination comes in transmission. You no longer focus the light on the tip, you focus it on the sample. But then still there is a tip which is in tapping mode, it scatters the near field and all the possible background, and this scattered light is collected. So the benefits of this transmission mode, that there is almost no disturbance caused by the tip, because you illuminate from the opposite side, and it's also polarization of the electric field is orthogonal to the axis of the tip. That's why it makes your life really simple and easy. And like another advantage, that it's easy to read out the near field, and it's simple simulations to support your measurements. And to demonstrate it, usually when I have some sample, for example, here's antenna in measurements, to simulate it and to correlate with measurements, what I do is I take this antenna, illuminate it with plane wave illumination. There is no tip in simulation at all. And then you calculate your full field distribution and simply take the normal component of the near field. And you can take it at 10 to 50 nanometers above the sample. In principle, this normal component of the near field is kind of quasi-static. So it doesn't matter actually at which altitude you take this component. It's only like a small blurring will be. So another advantage of this transmission mode is s-SNOM, that, for example, if you have waveguide, it could be two-dimensional or just planar waveguide, then you want to excite it in a different place, and it is possible with this transmission type s-SNOM. So for this waveguide, we have a gradient to have a larger excitation efficiency. And here you have independent control of the illumination beam. You have control, you can change it, position, polarization, and shape of the illumination, which you cannot do in reflection mode. In reflection mode, you only can shine to the tip. And yeah, you can say hypothetically, there is a little bit of tunability. In practice, there is nothing. Here, it's fully independent illumination and collection. And then, like the scanning is done like in like all near-spec systems. It's only the sample is moving during the scan, And for waveguides, it matters that during the movement of the sample should not go out from the illumination beam. And for this purpose, I think first we tried ourselves to do synchronized illumination during the scan, and later it was implemented in near-spec. Hopefully one of you used that in your transmission modules. Yes, so now zoom out. What the system looks like. You have laser, illumination is done with bottom parabolic mirror, and collection is done with top parabolic mirror. And again, you have detection and demodulation. So when the tip is in tapping mode, demodulation gives you background-free near field. Then you also have interferometric detection or pseudo-heterodyne detection. So you have reference arm where the beam path is modulated, which gives you amplitude and phase of the near field. So there is a difference between transmission mode and reflection mode in terms of interferometer type. In transmission, it is Mach-Center. In reflection mode, it is Michelson interferometer. And yeah, in some cases, there is it is important which type it is, but in general, it's simply there are two different types of interferometer schemes. Yeah, then next, let's compare all the advantages or differences between these two modules. In transmission mode, there is almost no influence of the tip. And then you have full control of illumination. And it's simply a simple interpretation of the measured near field. You don't need to include so many unknown tuning knobs, tuning parameters to interpret your measured data. And then I would claim it's best for waveguides and it's great for antennas. In reflection mode, there are still some advantages left, which is it is simply in alignment because the interferometer is a bit more simple. Then it is a bit more stable. Again, because of interferometer, it is shorter arm. And it can work in non-transparent samples. I think that's the major advantage compared to transmission mode. And it probably is cheap, I don't know. Yes, but there is a, okay. So the main difference, which I was not mentioned previously, it's applied for waveguides, difference between the transmission mode and the reflection mode. As you heard previously about polaritons, polaritons and waveguide modes, it's the same. In polaritons, the decay of the field, there is always this geometric factor. And it's 1 over x to the power of either half, which is square root, or 1. It is because they're usually square root because the polaritons are excited by the tip and they spread like cylindrical wave and you have this geometric decay. While in transmission mode, you excite a purely plane wave and there is no other decay. So it's simply decay because of the propagation losses of the mode. And as a conclusion, I have a statement here. It's a little bit suicidal statement for me, that transmission mode gives you precise measurements and reflection mode gives you imaging. Well, before you pick up your Rotten Tomatoes to throw at me, let's move on. I promised, the title promised that I will talk about nanoantennas and waveguides. So about nanoantennas, I have this very simple example. I use it for alignment and kind of calibration of the system. It's very simple. It's gold disc on a glass substrate. And you can see sizes here. You illuminate it in transmission mode with a normal illumination. And then this white arrow here, it shows you incident polarization. And the treatment of near field is simply the normal component of the electric near field. And what you see here, two hotspots with opposite phase, like a dipole antenna. It's a little bit not symmetric, as you heard before, and it's not as simply just some background addition. It's a little bit different. It's more like indirect illumination, but in this case, it's indirect scattering. So when the tip is on left side, it scatters to the right, so the top parabola is somewhere here, actually here. Then it scatters to this side, and then a part of gold disc kind of helps to scatter a bit more. When the tip is on the right side, there is nothing, well, the glass is not so much reflective, so the scattering is a bit less. So that's why, yes?
You have a metal tip.
Yes, it's metallized tip.
If you change it to a dielectric tip.
It's the same. I mean, about the asymmetry?
Yeah, in this experiment.
Yeah, it's the same, just lower signal. But the distribution is pretty much the same. So it doesn't influence much here. Yes, then you can also measure dielectric or photonic antennas. Yeah, and here is something we measured, but then we decided we not published. It's not so interesting. It was silicon rings on a glass. And here the incident polarization was vertical, like that one. And again, for antennas, the first response you would expect in this normal component of electric field is dipolar response. But here it's a bit asymmetric. It's a bit of a kind of weird phase distribution amplitude. So we, in other project, we had only silicon disks, and then we speculated that in near field you also see other components of in the measurements you might also see other components of the near field. But I simply believe it's a bit speculation. So it is a bit weird because here the dominant, in dielectric particles, the dominant field is inside dielectric and it is lateral. So the normal component of the field, which the system picks up, it's not dominant, and it's weak, and yeah, it is perturbed. Or you can have many speculations here, let's say. Then quite an often situation I have that some of my colleagues, they do far-field measurements or simulations of antennas. It could be single antenna or it could be metasurface, and they measure scattering or absorption or any other type of spectrum, like here. And then they come to me and ask, can you do the same in the near field? And here I should say no. And there are several reasons. So there is an issue with normalization, and then the near field distribution, it changes with wavelengths. And 2D scan, it's only good for single wavelengths unless you have this point spectroscopy, which Yasin told yesterday. But there is a way around. So instead of wavelengths, you do a sweep in size. That's what we did here in this paper. It's actually not the main part of the paper. It was in supporting information. So here it was this nano rod, nano brick antenna, like that shape. And then we kept the same cross-section, but just increased the size. And here the antenna length changed from 100 to 2,000 nanometers. And then, well, it was actually quite crappy fabrication, but in simulations you can see that there are, at some antenna length, you can see the near field becomes larger. Well, it's a little bit agreeing with experiment. So at this length, you can call it a resonant length of antenna at this frequency, because the frequency or the wavelength of light is fixed. And actually, similar work, but 5 years ago, was done by Rainer in the reflection setup. So as I mentioned, whatever I will tell today, it's not only limited to this overlap of 3 circles. So in reflection setup, you can also do pretty similar stuff. So it was similar nanorod antennas of different lengths. So instead of wavelengths, you sweep the length and you find the resonant length of antenna. So that's the only thing you can do. And overall, but for this simple geometry, I would say it's so simple. Do you really need to do near field? So my take-home message that, to be frankly speaking, near field measurements, there is no scientific results in near field measurements of antennas. So of course, you can do imaging here just to produce imaging. And it should be, it can be like a supplementary results to, so the main scientific research should be done somewhere else, for example, by measuring spectra of antennas. And you, with near-field setup, you can supplement it with nice, colorful imaging, and then you can push to high-impact journal. Yes, but the story is different for waveguides. When you have waveguide, like here, just nice demonstration of plasmonic waveguide. It's a big stripe, it's tapered to the nanowire, and then it's defocused to a big stripe again. Yeah, you measure the near field. It's very easy to, this is just raw near field measurements. It's very easy to understand what's going on there. And here, one can measure, not image, one can measure first by doing mode analysis. One can see number of modes and the mode wave vector, also effective mode index, and propagation length. And as a second step, one can measure reflection and transmission through the junction. Like here on the left, the junction is too long, but on the right, you have this short junction, and you have here the white stripe. This region you can analyze with to see the number of modes, and one can see how many of them reflect, and you can find this reflection coefficient, and also transmission to the second part of the device. Yes, and then about the waveguides, when you have plasmonic waveguides, it's very, very straightforward to read the near field. And here it's, again, just nice demonstration. It was this gold, 30 nanometers gold stripe on glass. Here it was grating. I shine the light here on the grating. It excites plasmons, and they propagate. And here they simply focus into nanowire and go through there until they die. Here it is a termination, and the plasmons, they are too much confined, that therefore they cannot scatter out, they back reflect to the waveguide. That's why you see those fringes in amplitude. And the phase, instead of gradient, you have just phase plateaus with 0 and pi phases. And then final, it was antenna terminated taper, so it's probably, maybe it's hard to see. It's a small section of nanowire with a gap. And ideally, it should be that all the power coming here, it should either be absorbed or scattered, and the field enhancement should be the highest here. In experiment, the gap was a little bit larger, and therefore you have some back reflection. But again, like these two lines, it's experiment. In the bottom, it's simulation, and you can kind of see whether it corresponds experiment to simulation or not. Like to my eye, it's pretty good correspondence. And in simulations, it's simply the normal component of the electric field, and no tip included. And plane wave or focused beam, no, actually it was not plane wave. You just launch the plasmonic mode and propagate it towards the taper. So plasmonic waveguides, everything is great, good match with simulations, because the dominant near field is normal. When you have dielectric waveguides, you can still do measurements of the waveguides, but you need to keep in mind that dielectric waveguides, the fundamental mode is in plane, like shown here. So the electric field is horizontal, while your setup picks up mainly the normal component of the field. And normal component will be weak, and it will be like these white arrows. So it will be opposite directions on both sides. That's why in the experiment you see this one line on one side of waveguide, another line on the other side, and they are opposite in phase. And in dielectric waveguides, people use it because they propagate like much longer than you can fabricate, basically. So they don't die somewhere behind the image. So if you do termination, they will back reflect. That's why you see fringes. It's basically standing wave. You have forward wave, and somewhere far away, it is back reflected and forms this standing wave. So the take-home message here: dielectric waveguides and antennas. The near-field characterization is indirect, because the dominant near field is in plane for dielectrics. Yes, now about precise measurements with s-SNOM. That's the work we did a few years ago with Jonas. Here we used the gold flake, and the idea was to find actually the limit of optical losses in gold. So we are speaking about plasmonics, and in plasmonics you use noble metals to have as small losses as possible. And the losses comes from the material, not material, but basically how good you are in fabrication. And in our lab, we learned how to fabricate, how to chemically synthesize these gold flakes. They are monocrystalline, and we believe they are atomically smooth, but probably we will ask Lucas to check if they are atomically. In IFM, they look super smooth. Like the RMS is below 0.2 nanometers. But I suggest there might be some atomic steps there. And actually, if you want some, we can ship you. It's very easy to fabricate them. So what we did here, we illuminate the laser on the edge of the flake, and here you have this momentum matching because of line defect. So it excites this plane wave or plane beam of plasmons propagating on the flake. And then you scan on the flake surface. And here what you get, again, like just raw data from the setup, amplitude, and real part of electric field. And then I forgot to mention this animation, or how you do it. Real part is amplitude times cosine of the phase, and then for each frame you add same phase shift, basically, between frames. And then you can have this nice animation where you can see the propagation of waves. But here the fringes are so small that probably it's hard to see. Everything is blurred. So what you can see here, it's like a plasmonic beam which propagates on on this gold flake, it eventually decays because of plasmonic losses. There is no other losses, simply absorption in metal. And then we calculated the mod parameters, is real and imaginary part of mod index, and then propagation losses, and we compared to the databases, and we found out that the mostly used database for single crystal gold, it actually gives you wrong numbers. It's not as good as it is supposed to be. And there is another database which is better. But since it's summer school, it should be practical. It should not be about advertising your own papers. So about practical stuff. Well, first of all, you always see this dispersion curve of polaritons like that one, light line and polaritons, if whatever nature they are. And here frequency and wave vector here. In fact, in practice, I don't really like this way of dispersion, and because the question is how far the polaritons from the light line. And here it's a bit hard to see because it goes asymptotically to the light line. So instead, I use this so-called effective mode index or normalized wave vector. So instead of using wave vector k, you divide it by k0. And then you have this effective mode index. It is complex valued in general case, and then the real part of the effective mode index is simply your kind of relative confinement. It's a ratio between free space wavelengths and polaritonic wavelengths. Okay, the good part that it is unitless, so which means to some extent you can compare polaritons from different natures, from different regions. Another thing I do in visible and telecom, that instead of using frequency in electron volts and inverse centimeters, I use wavelengths in nanometers or micrometers. So this dispersion curve is then transferred to this one. So you change frequency to wavelengths, and you change wave vector to effective mode index, this one. And then you can see how far your polaritons away from the light line. And for plasmons, they are not super confined. They are away by here. In the good scenario, it's by 10%. and then when you for long wavelengths, it's just few percent or less. In mid-infrared, it's even worse. It's almost like free space, very close to 1. Yes, another suggestion is about another factor, propagation length. I used to the definition of propagation length as decay by E times for the power, or it should be squared. So the power or intensity proportional to the E squared, then here it decays like this exponent, and basically I use this definition of propagation length. And with this definition of propagation length, we can define figure of merit, or quality factor, again, to compare different polaritons from different ranges. And the definition is very simple to enforce. It's how many wavelengths, polaritonic wavelengths, inside propagation length. So you divide propagation length by plasmon or polariton wavelengths. And it will be this factor. So it's the same as Pablo showed, divided by 4 pi. And the good part of this definition that whatever you study, it could be graphene, it could be gold plasmons, it could be phonon polaritons. For very confined polaritons, it's close to 1. So like earlier Pablo showed for graphene, it was this one was 24. Okay, it was 2. So you don't need to remember the numbers. The numbers are always around 1. Yes, so let's move forward about practical aspects about precise measurements with s-SNOM, which we did here, and tips and tricks. So first was about adjusting the incident laser beam to have the best plasmonic beam. So it should be perfect Gaussian beam incident on the sample, and it should be wide enough so that you don't have divergence. Why? Because, well, we want to prove that the gold is better than what is in database. That's why we try to avoid any like tuning knobs, any free parameters. So if you don't have divergence, then you don't need to explain why your field decays more than it should be. So it is more convincing when you don't have these fitting parameters. Then the scan size should be also adjusted accordingly. So basically in width, it should accommodate the whole beam. And then in length, it should also accommodate the beam with its decay. So it should be more than the propagation length, or maybe more than a couple of propagation lengths. And finally, the tip, which might be probably generally used about improving detection. So the advice here is to use low noise detector and balanced detection. So, and improve interference. And here, I just want to note you again, because it's summer school, you should learn, and here's a couple of equations. It will be no more than that. There is a bit of difference between 3-dimensional and 2-dimensional Gaussian beams. Of course, it looks like a big equation with many unknowns, but if you look, it's very simple to understand. So it's basically multiplication of several factors. First is scaling factor, because when beams diverges, the electric field drops down. Then the next exponent function is just the amplitude factor, it's just the form, the shape of the pulse is Gaussian form. Then it's transverse phase factor. When instead of a plane phase, you have curved phase like from a point source. And then this small longitudinal phase factor, usually people ignore that. And then usual plane wave factor. So this is in 3-dimensional. You can find it in all textbooks. In 2-dimensional, it looks very much similar. And at first glance, you cannot see a difference. But the difference is first in scaling factor, because this one diverges in area, and 2D beam diverges in line. And another difference is in this longitudinal phase factor, and this phase shift is called Goi phase shift. Probably it's pronounced differently. And it's a phase shift in the waist of Gaussian beam. But usually people ignore it, no one cares about this phase. And yeah, but in general, I would recommend to make Gauss to be your friend. There is also an alternative way to write down Gaussian beams in complex numbers, and it's easier, I mean, it takes less space. Not sure that it's easier for practical application. Yes, coming about practical aspects about improving detection and low noise detector. For visible and telecom range, you have a choice. You can have a large area detector, which will have high noise, or you have small area detector, which have low noise. By the way, this is a repetition from like 1 year ago. It was Near-spec workshop. So if you was not there, yeah, you can take a look. There is a video on YouTube, I guess. So the question is which one to choose. My advice would be to use both, because you can use large area for alignment. When you do alignment, you need to change the beam, and you don't want to miss the focusing on detector. So you can first take the large area detector and do the alignment of the interference arm and the top parabolic mirror. And then, when alignment is good, you switch to the small area and low noise detector and get really good results. There is also a bit of gain versus bandwidth and AC and DC coupled detectors. You can look, if you like, in this video from the Near-spec workshop from the last year. About balanced detection. Now, if you have the source which is a bit noisy, like shown here, the intensity oscillates in time. In usual setup, you will have this noise in the measured near field, in measured high harmonics, and then it becomes like useless. There is an easy solution for that, is to use balanced detection. It works like following. Like first, you take a small part of the incident beam and put it to detector. And then the rest you put through the s-SNOM and collect this scattering plus interference with reference beam by another detector. And then the noise of the source will be in both measurements. And this balanced detector, it does the following. It first takes the difference between two measurements, and here's alpha is used to balance both signals, because you can remove the noise only when the signals are balanced. And then it amplifies this difference. And everything here is in one box. And as the output, you have no noise, and additionally, you don't have DC offset, which might be a problem for saturation of detector. And here's an example of balanced detector, which I use in my lab. This is visible. The same is for telecom. There's also ones from Newport. I think they work the same good as this one. Yes, now about improving interference. Like it was spoken many times during the summer school, that you have interference between the signal or scattered beam and the reference beam. And you always see it like following, like sum of the two electric field squared and this interference term. In fact, it's a bit incorrect, because you should include this interference parameter gamma, which is from 0 to 1. So when we do demodulation, we are looking for this term. So we need to maximize this term. And this term is gamma is maximum equal to 1 when you have the best case interference. And here you need to keep in mind that you have the best case interference when there is a complete coincidence of these two beams, which means this signal beam and reference beam, they coincide, first of all, in angle and position. That's kind of obvious. But also they should coincide in polarization. It's also kind of obvious. They should also coincide in size and phase front, so there should be no divergence, or they should diverge in the same way. And also they should coincide in beam profile. So if your beam is not perfect Gaussian, then you might have a trouble. Again, like make Gauss to be your friend. And if you have non-monochromatic sources, they should also coincide in time. Which it's not about only pulse sources, but it could be like, for example, output from OPO. It's quasi-CW source. It's still like it's better to work around 0 delay line when these both pulses coincide in time. Then you have the best case interference. Now about making Gaussian to be your friend. I mentioned yesterday, I think, about using fiber-coupled laser. I think it's really helps a lot. And here's the lasers which I have. And you see the fiber output. It's telecom laser. You can also find the same for visible ones. And you use it in pair with fiber collimator. And there are two options. One is kind of goodish. It's this adjustable collimator. The good part of it that you can change the beam size. But in fact, in my lab, I use reflective collimators, and I call them best solution because they are ideal achromatic. They have ideal achromatic design. And the benefits of using fiber-coupled laser with collimator, of course, because you have the almost perfect Gaussian beam shape, which is good for interference and good for focusing to have. If you need the tightly focused spot, then you need to have perfect Gaussian beam. And it's also easy switching between sources. So if you have many sources in visible telecom range, you can just unplug one fiber, plug another one. You don't need to redo alignment. I also tried to use this. There is a special fiber for mid-infrared, but it's still ongoing project, let's say. Yes, if your sources are not fiber coupled, then it's relatively easy to do fiber coupling. So what you need is a couple of mirrors and three-dimensional stage with objective, and usually it's 20 times objective is fine. You can get the cheap one and just attach the fiber to this 3D stage. And then, like from practice, if you are good in coupling, then you can get like 50% coupling efficiency to the fiber. But remember to use a single mode fiber, and sometimes polarization maintaining fiber is even better. Yes, now about near-field data analysis, which I do. Well, here's an example where there are these plane waves, different plasmonic waves propagate. It's not the best example because sample was not as perfect as in previous case. You see here amplitude, phase, and real part of the field. And here it was the design of the structure. So it was designed, so incident wave was from left to right. And it was designed in a wave that to excite these gap surface plasmons, very highly confined plasmons, to propagate in one direction and not in the other one. Therefore, you have this different asymmetric picture. In going up, there are fringes, they are more tightly spaced. Going down, it's SPP, they are more sparse. So what I do to analyze near-field data? First, I do one-dimensional Fourier transform. So I take first half of the image where the waves propagate up and do one-dimensional Fourier transform. And it's a plane waves. You don't really need to do 2D Fourier transform. I don't really see a point. You just do one-dimensional Fourier transform. You change one axis to k and keep this axis as the same, or real space as it was before. And then you do the same for the bottom part. And you can see which waves propagates in which direction. And here I use, and I also recommend you to look into it, I use this so-called extended discrete Fourier transform. This Vilnius Liepnis, made this file for MATLAB. So, okay, I will tell you a bit in the next slide. So then I sum up along all the cross-sections, and here you can see the peaks, you can see the modes which basically propagate in the system. And here, instead of k-vector, I use this normalized k-vector, effective mode index. And the SPP, they have effective mode index around 1, as expected, and this so-called gap surface plasmon, GSP, they were highly confined. Of course, it's not even close to graphene, not 100, but effective mode index around 6 for visible and telecom. It's also kind of record high confinement. Yes, and the next steps, I don't use Fourier transform to get the numbers. I use it for filtering in Fourier domain. So, for example, here I was interested in gap surface plasmons. I apply the window here, remove all the rest which is outside, and then I do fitting with a complex exponent already in direct space. So I do inverse Fourier transform, get a direct space field, and do fitting with complex exponent. Yes, about EDFT, extended discrete Fourier transform. What it does. So in our case, we watch about the surface, like polaritons. It's exponential decay in waves, so it oscillates and decay. So, for example, this is your measurements. And usually measurements, they are limited in space. It's not infinitely long. So if you would have infinitely long and without noise measurements, then ideally you will have this I call ideal Fourier spectrum, when the center one is exactly at the real part of propagation constant, and the width is imaginary part of propagation constant, which is lost. But since we have a limited data, we can do only discrete Fourier transform, and we get these points. So as you you can expect it, you have only few oscillations, therefore the resolution is really bad. And also the peak, what you see, the peak looks like it's a bit broader than it's supposed to be. Much broader, I would say, simply because you have a limited range in the direct space. And to some extent, to understand why it works wrong, why it's not the same point just along the same line, this discrete Fourier transform, it considers to be a periodic structure. So it assumes that your field behaves like that one, which in fact it's not how it should be. It should be just exponential decay into infinity. Okay, so what can you do? You can do high resolution discrete Fourier transform, also called zero pattern. When you artificially increase the resolution and fill zeros for the rest part. And then you get this spectrum in Fourier domain. You still have the same issues. You have the issue of resolution, you have the issue of broadening of the Fourier spectrum. Again, because if you do inverse Fourier transform, it will be this, it's not a perfect exponential decay because it fills with zeros. So what extended discrete Fourier transform does, it does iterative filling of the remaining part. So you apply it again with improved resolution. So you want to improve resolution by 5 times. And you have this extra space. And it does iteration by iteration. There is some black magic behind. So it fills the holes. And eventually, if you apply inverse Fourier transform, that would be the field it assumes. It's already here, it looks kind of close to this exponential decay. But again, it's whenever it's discrete Fourier transform, it is periodic. That's why you see exponential increase before coming to the next period. But when you look at the spectrum and compare it to ideal case, I'm not sure you can actually see this orange line. It looks very close to the ideal case. And remember, I don't use, and I don't recommend you to use Fourier transform spectrum to exactly measure the propagation constants, the k-vector and losses. I recommend you to use it for filtering. So you apply the window and filter and keep your mode separately from all other modes or from the noise which you have. And then do the fitting in direct space. Yes, that's what I just said. Just a little bit another practical aspect, since, I mean, we are not talking about scientific papers. I found this perceptionally uniform color maps a few years ago, and I really like it, and I would like to share this idea to you. Maybe you will also like it. The idea is following, that the standard color maps, they are not uniform for our eyes. Well, also probably projector changes the colors. But you can see that some spaces there is not much contrast, and in other regions the contrast is too high. And the idea behind this project, I think it's kind of research or scientific project, was to have perceptionally uniform color maps. So you have for your eyes, for your perception, of course we have a slightly different perception, but let's say statistically average human being can perceive it as uniformly spaced colors in these color maps. And they look similar to standard ones, maybe not so bright, but more uniform. And here's some example to apply to my data. Okay, it's not really good example, but at least you can see. So this is standard color map from Gaussian, and here I applied this uniformly spaced color map. And you can see that here the bright part, it's saturated. You don't see these tiny details. And it's not because it's saturated in the color range. So here the color map goes to the maximum of the data. It's simply because colors here, they are, yeah, you also need to look at the screen. It works a bit better on the screen. But it is, seems to be saturated. When you apply this different map, it's more uniform, you see more details. So this, what's called vendor color maps, it's good if you want to hide something. You can saturate 0, you can saturate the maximum, and you can hide whatever you don't like. But if you want to be frank to yourself and to others, and you want to show all like raw data as it is, with all the defects and details, then I highly recommend you to use these uniform color maps. And the ones which I use, like previously I used those color maps for amplitude, phase, and real part, and then I changed it to these uniformly distributed maps. And they look pretty much similar. And if you need, I can share you Gaussian files with gradients. Now, last bonus before I end, it's about non-transparent samples in transmission mode. As I mentioned, it's a benefit of reflection module that you can use non-transparent samples, but there is also a way around to use non-transparent samples in the reflection module applied to waveguides, and it's called end-fire or butt coupling to the waveguides. Basically, you have a waveguide which extends to the edge of the sample. It's usually cleaved edge of the sample. And to couple the light in the waveguide, you need to focus the light on the edge. And solution is simple. Use 45 degrees mirrors. And in transmission module, you have this normal illumination. And with this mirror, instead of normal, it becomes in plane direction of the field. And then you can focus at the end of waveguide. And first practical realization was like following, just a bit of green clay and this mirror, which is nothing more than a silicon wafer with gold on top. And then the sample you just glue to this double-sided sticky tape. So this is what it looks like from the side. And here you illuminate your laser, and it focuses at the edge or at the end of the waveguide. Then, since it's worked, I went a bit more to 3D printing, and there you can like attach, put the same mirror actually in this socket. Here, how it looks from the side, and then you illuminate sample from the bottom, and you have this end-fire coupling to the waveguide. And here, actually, these bright spots, there are many different waveguides. So, take-home messages. It's already end. You will be free soon. So transmission mode, I believe it's the best for waveguides and good for antennas. For antennas, actually, nothing is good. Only far-field spectroscopy. Yeah, so near-field is only imaging for antennas. Then make Fourier be your friend. It's actually Fourier, it's everywhere. And yeah, also make Gauss to be your friend. Yes, and then, so with that, I would like to thank Monica, first of all, to Rainer and Adrian for organizing this event, and to you for your attention. And I'm really glad that you all, most of you, stayed here until the last minute. Thank you.
Thank you, Vladimir, for sharing all these practical hints and so on. So questions? Yeah, there.
Oh, thanks. Thank you. Very nice talk. I have two questions, actually, on Fourier transform.
Yeah.
So the first one is, so you recommend using the Fourier transform to filter real space data and then fit the real space data. It's because you noticed that you have some shift between the fitted peak in the Fourier transform and the one that you obtain from real space fitting. And I don't know, the second question is, do you use also the phase channel to compute the Fourier transform, or you use only the amplitude channel?
First of all, of course, you use phase. Always use all the data which you have. And for the phase, if you don't use the phase, you always get symmetric Fourier transform, and you don't see the direction of propagation. Only when you use phase, you can see that the wave propagates one way or another way. So always use phase, and in principle, use all the data which you have. Never ignore or discard the data. About the point, why do I need this fitting and not use Fourier transform? First of all, because in Fourier transform, there is always this limited resolution in K. Also, if you want to know losses, then in Fourier transform, it's the width. And it is highly affected by the range of your sample. And about the resolution, why fitting is better? Well, Fourier transform is kind of universal tool. You can put whatever you have with many different modes there inside. It will show you, and it will distribute these different modes there. And so it is universal, and as a side effect, you don't have this enough resolution. But if you know that it's only one mode which is present, like here, for example, this sine wave, you can fit this sine wave with very high precision if you don't have noise. So you are not limited to this resolution limit by Fourier. But only if you know exactly, if you are sure that it's only one mode which is present. Then fitting is better.
Oh, I see. Thank you very much.
It's also free.
Thank you for the nice talk. I also have two questions. So the first one would be about the waveguides. And so did you fabricate them so that you can actually see the field leak out of them? Was that like when you fabricated them? Like, did you have this as your in mind?
To some extent, yes, but only rare because usually there is evanescent tails. Like in plasmonic wave, no, okay, it's for all waveguides. Usually there is always some plasmonic tails coming out. But for example, for the case when it was this gap waveguide, I quickly went through it. The configuration was like this bottom metal plate, then the tiny dielectric spacer, and the top metal plate. And this gap mode, it propagates inside this spacer, like a capacitor. So if your top metal plate is too wide, then your evanescent tails are not reaching your tip, because the tip picks up the field where it can reach. Therefore, here you need to keep it in mind, and then as a top layer, it should be thin enough. So in this case, it was from 30 to 50 nanometers gold. So it was very, very low electric field, very, very low efficiency, but because, I believe mainly because we have this interference with strong reference beam, we can see this very low fields. Yes, and...
Thank you. And the other question would be, so you said that the tip does not, or plays less of a role, or there are less effects by the tip in transmission than in reflection. So what is the physical reason for that? Like, how can we visualize this maybe?
About the influence of the tip or what?
Yeah, exactly, the influence of the tip, yeah.
Well, the main hand-waving argument that the tip has a strong dipole polarizability along its shaft, along z-axis. So if you have the light with polarization, which can be projected to this z-axis, then you excite this tip antenna, basically. And then you have like a mess there. Not mess, I mean, people work there in reflection mode. There is a way around, like you, in reflection mode, you can say, and also S-polarization to avoid this excitation by the tip. Yeah, in reflection mode, the issue that the incidence is also at some angle. So instead of dipole, you see some quadrupolar kind of distribution, which is not present here. But in transmission mode, it's very simple and straightforward. You have just normal illumination with polarization, which is always orthogonal to this z-axis of the tip. And therefore, it's almost no influence from the tip. And like you can make theoretical models there, but from practice, I never include tip in simulation when I want to compare the experiment with simulations. It acts as it's supposed to be for the probe microscopy, that it probes without deformation of the field.
Thank you so much.
So, in the end, for this wonderful gold flakes which you have in Copenhagen.
In Odense.
Yeah? Oh, that's all right. Denmark.
Yeah.
Sorry. I would like to compare the accuracy which you get from the plasmon propagation experiment with ellipsometry, because in the visible you have very highly accurate ellipsometers, and what they can tell you is not only the epsilon, but also the scattering. So if there is still some, as you say, some atomic steps or something, you have some scattering. And so in ellipsometry you have this, you know, this Müller matrix and so forth, which gives you the two things separately. And have you ever compared it? Have you taken one of your gold flakes to some with highly available, fantastic polarimeters?
I would really like to compare it, but there is no ellipsometry measurements of the gold flakes. And the answer is because the size is still like 100 microns, and for ellipsometry they illuminated with a free space beam, and only it's slightly collimated, slightly focused beam. So they require samples with larger area. They cannot use, there is also imaging ellipsometry, it has its own drawbacks, but if someone could do ellipsometry of this gold flake, yeah, they are welcome to do it. But so far, there is no ellipsometry of gold flakes.
So it's a size problem, you would say?
It is a size problem.
Oh, yeah. Okay.
Also, to some extent, I'm not familiar too much to ellipsometry. I'm just theoretician in this practice. I don't really think they really measure the scattering. I mean, sometimes when the rough surface, it's incorporated in additional losses to the gold. I'm not sure you can decouple.
Dimitri said something. So it's really possible.
Okay.
There's a lot of modeling involved in the reconstruction. Surface layer is one ill-defined element of this model.
For example, like that one which we discarded, the common reference by Ullmann. Why it is common reference? Because it's probably it's a long way. No, it's here. It is common reference for these synthesized gold nanostructures or monocrystalline structures, because here it's specifically mentioned that it was single crystal gold, and everyone thought, and they measured by ellipsometry, of course, because that's the most reliable technique. And everyone believed, okay, it's single crystal gold, that should be the proper result for this chemically synthesized single crystal gold. In fact, there, the single crystal gold for ellipsometry should be large size, so they bought this big crystal, and it was mechanically polished. So it was not smooth. It was rough, which is eventually gave these larger losses in epsilon. And I'm not sure that you can kind of decouple. Well, again, like I'm not expert in ellipsometry.
Okay, so let's thank Vladimir again for his talk.